Welcome to the second lecture of part 6 on survival analysis, and in this lecture we're going to talk about non-parametric survival analysis. In this lecture we're going to talk about the life test procedure, which is a non-parametric method of analyzing survival data or time to event data. Now let's say we have 40 rats that are randomly allocated to two groups of 20. In one group, they are exposed to a carcinogen, and in the other group, they are exposed to a placebo. Now, of course, the outcome variable was the time in days from randomization to death. Let's start off with the data. We have our data statement. As usual, our data set is going to be called exposed. We're going to have our outcome in days. We're going to have the status here, which is going to be whether they survived or died. We have our treatment, of course, which is going to be with the carcinogen versus the placebo. And in this case, we're going to have the sex of the animal. Now we have a new statement here, actually a new statement up here called proc format, where we're assigning a label to our data. So for instance, for treatment, it's going to be 1 is going to be drug X and 0 is going to be placebo. We then include the format statement or option, if you wish, in the data statement, and this is going to tell the data statement. So when you're creating the data set called exposed, please use the labels for this variable. Okay, the lower portion is our proc life test statement. There's a lot going on here. The ODS graphics on statement just says to please use the ODS graphics, and that's to output the plots. You turn it on at the beginning, you turn it off at the end. Your proc life test looks similar to the proc life reg that we used. The difference is we have an option here for plots. We're saying please output the plots. Our outcome is very similar here in the sense that we're asking in terms of the outcome in time. It's days this time, and we're associating it with the status of the animal. But so instead of using sensor, so another variable that would say sensor 1 or 0, as I discussed, I think in the last lecture, you can use the status. In this case, the status is dead or alive, essentially, right? And so you can tell it that the censorship is going to be when the status is 0, meaning that the animals are still alive. So the event has not occurred. The strata statement is simply to say there are two groups, and they are grouped based on this class variable called treatment. And we would like to compare, the time between, or the mean time to event between the two levels in treatment. So on to our output from proc life test. The first thing we will look at is the summary of the number of censored and uncensored values. So this is just pretty intuitive. You have the total number of mice, which is 40. You have 36 of them that failed, meaning they had an event. And then there was 4 of them that did not have an event before the end of the study, or they were lost to follow-up. And so we have 4 censored mice. You can also see, by stratum, how many, failed and how many were censored and what the total was. If we move over to the right here, this is your table that gives you your survival time and probabilities. So you see here's the time in days, and here are your mice basically that failed at a given time. And then, of course, the difference, which is the number of mice left. In this case, it's for drug. So that under treatment for the stratum, you have for mice that receive the drug. I highlighted in red, and boxed out in red, the mice who were censored at a given time. So for instance, this mouse was censored at 224 days, so basically lost to follow-up. And this mouse who followed all the way to the end and didn't have an event, and so they were censored at that time, and it's like 378 days. Under your survival here is the probability of survival. Of course, at the very start of the study, when all the mice were alive, the survival, of course, was 1 and the failure was 0. And then as you move down, your survival probability decreases as you move along or across the study, and your failure probability increases. inevitably. Okay, finally here you'll have the summary statistics for the time variable in days, of course, and this is going to give you the mean time for this group, so these mice that are on drug X. What was the mean survival time? It was 271 days with a standard error of 11.8. And then it also gives you here your quartile estimates, whereas, for instance, this is the median time, so 50%. The median time was 256 days. And so inevitably, it's usually advisable to give your median time in terms of time, your estimates, just because you're not sure if your distribution is normally distributed in order to provide a mean. And the other problem is this: you see the note here, the mean survival time and its standard error were underestimated because the largest observation, so the one down here, 378, was censored, and the estimation was restricted to the largest event time. And so that's the case here. I mean, so it's clearly telling you, whoa, be wary of the mean time. So then you should probably be reporting your median time. Okay, now we'll move over to the other group. So the treatment is placebo in this case. Very similarly, we have two censored mice, one at 237, one at 268 days. Once again, if we look over here at the summary statistics, you have the mean time of 235 with a standard error of 10.2, and you have a median time of 235.5. And so interestingly, you'll see here that your last mouse was not censored, and therefore you don't get that warning of an underestimate. So here's one of the graphs that pops out of your SAS output, and it's probably the graph that you were expecting, and that is the survival curve. So it's a graph that plots the survival probability on the y-axis from 0 to 1 with time, in this case days, which is from 0 to a maximum of 400 days for this study. Now your two curves are for your two strata, one for drug in blue and one for red for the placebo. And in order to identify the censored individuals, the censored subjects, the censored mice, SAS puts a little cross mark. So there were two for both placebo and drug groups. Here's one, here's two for the drug group, and here's one, and here's two for the placebo group. Now finally, we also have here down on the bottom the number of remaining subjects in the study by time. And so of course at time 0 you have the full cohort of both strata, so 20 and 20, and then at the end you have 0 because all subjects have been accounted for, whether they have had the event or not, or censored. Over here we have output the test of equality over the strata, and what this does is it tests whether there's a significant difference in time between the two survival curves of your strata. The two tests you're going to want to pay attention to are the log rank and the Wilcoxon test, and we're going to come back to those in subsequent slides. As you can see, for both of them, there is a significant difference between the two, with the mice on drug that are surviving longer than the mice on placebo. So the next two graphs that pop out are graphs to assess the assumption of the Kaplan-Meier estimate and whether or not your data fits those assumptions. And in this case, the most important one is that the survival probability is constant between intervals. And an interval is literally the time between two survival probabilities, not including censorship. So the first graph is your negative log of your survival probability on your y-axis, time on your x-axis. And what you're looking at here is by strata, how constant, if you wish, is your survival probability. And so by constant, you're going to be looking for linear relationship. So if it looks linear and the two strata are basically parallel, that's a good sign. The next graph is the log of the negative log of the survival probability. And once again, what you're looking for is a linear relationship, so a straight line for both strata, and you want both strata to be parallel. So you want the same linear relationship, same slope between your two strata. In this case, this would pass. So the results of the two sampled tests, you remember a couple of slides ago, we had those rank tests for homogeneity that were displayed. And we had two tests. I told you there were two tests you should be looking at, and that's the log rank and the Wilcoxon test, and both of them were significant. The drug-treated rats lived significantly longer than those on placebo. Now, because the survival curves for the two treatments differ primarily at longer survival times, and the Wilcoxon test places more weight on short survival times, it becomes less significant than the log rank test that is having a larger p-value. And you can see that down here in the comparison. Let me just get my pointer, sorry. You have the log rank test has a more significant p-value than the Wilcoxon test here at 0.0175 versus 0.0249. And that's because the Wilcoxon test places more weight on shorter survival times. So depending on what you're interested in your comparison, in the shorter survival times or in the longer survival times, that's how you're going to decide whether or not you should be reporting the log rank or the Wilcoxon. So in this case, we're interested in the longer survival times, and so we would report here the 0.0175 for the log rank test. Now, this is a summary, if you wish, where we've put together in one table, when we're comparing drug and placebo, in the time to death in these mice, you have a median time of 256 days when on drug, or 235 days when on placebo, so shorter on placebo. You have a mean time of 271 on drug and 235 on placebo. Here's your standard errors. And over here, these are your chi-square tests, your log rank tests, your log rank and your Wilcoxon tests, so log rank and Wilcoxon, and we explained how to choose between the two in the previous slide. Now suppose male and female rats have different survival rates, so meaning the variable sex is of interest. Therefore, we test the treatment effect adjusted for the sex effect. Now the variable sex in the strata statement is a stratifying variable, and the main variable, treatment, is now the group option. The test statistics for the treatment variable are computed by pooling over the strata defined by the values of sex, thus controlling for the sex effect. Now the notable option is added to avoid estimating a survival curve for each sex. If we didn't add it, then we would output a survival curve for each sex, but we're only interested in the difference in treatments controlling for sex. Now, if the variable sex is associated with the group variable treatment, then including it in the strata statement as a predictor will lower the residual variation and lower the p-value for the treatment variable. Here on the lower, the bottom portion of our slide is the code that we use in order to perform this test, and you'll notice it's very similar. However, we've included the notable option here. And in strata, we include sex, so the strata is sex, but then we're telling SAS that the group variable is treatment. So the second analysis, when we run it again and we look at the log rank and the Wilcoxon, again, you'll note that the log rank, or both of them actually, the p-value is smaller as expected. So what are the lessons learned? You may want to show that an exposure variable such as drug or diet is related to an outcome variable such as death or change in blood pressure, for example. And you may want to also include in your analysis variables such as age or sex for two reasons. First, if it is a predictor of the outcome variable, then including it in your model will reduce the background random variation, thereby reducing the standard error of the outcome variable and thereby reducing the p-value. Second, if the predictor variable is also related to the exposure variable, the size of the impact of the exposure variable may become larger or smaller. The predictor variable is then called a confounder. So this brings us to the end of lecture 2. Now in the first lecture we covered parametric methods, and in this lecture we covered non-parametric methods. So you're probably wondering, how do I make the difference, or how do I choose between the two? And as I said at the end of the first lecture, one of the biggest challenges of parametric modeling was that you needed to hypothesize about the distribution of your survivor function. And so that's probably the biggest differentiator between the two, is that if you do know the distribution, then you can certainly use parametric modeling. If you don't, then it's very challenging to do, because if you get it wrong, your model is extremely poor. In the case of non-parametric modeling, the assumptions are much less, much easier to satisfy, and therefore, in order to get an answer, it's much easier. So the non-parametric method is often used when just looking at or just needing the mean time or median time and comparing it between groups. But if you want to do modeling where you are adjusting for covariates, then the parametric methodology would be better for you or easier for you. But then, of course, you need to once again, make that or hypothesize about the distribution. So there is another solution, and it's called the Cox proportional hazards, and it's actually a semi-parametric method. And in this method, you can perform what you've learned in this course as a classic regression modeling, adjusting for covariates. But the assumptions, once again, are much easier to meet. You do not need to hypothesize on the distribution, and yet you are still able to perform a regression where you're controlling or adjusting for variables. What results from that analysis as well are hazard rate ratios, which are fairly common in survival analysis for reporting, especially in medical research. We're not going to cover Cox proportional hazards in this course because it is more advanced technique. However, I am happy to answer any of your questions if you are performing survival analysis and would like to explore the Cox proportional hazards. Now, next up in part 7 is going to be a short introduction to the use or the analysis of count data. See you there.